Section 6.3 we left off in the middle of, and we had talked about some things with multiplication and division, and we were at the point where we were going to talk about exponents. So to start with, the definition of exponents says that if we have a raised to the n power, it means we have a multiplied by itself how many times? N times. So however much the n is, and we use this for any natural number n, so we say that there are n of these down here. And we have 6 different properties of exponents, at least to start with, that we're going to take a look at. And what I want to do first is I want to help you remember these properties. And then what I'd like to do is I'd like to show you why they work. Okay? So I want you to keep in mind on your homework, I'm wanting you to just use the properties. I'm not asking you to re-establish the fact that we've done in class. That's not the point. But I want you to have seen these and why they work, because somewhere, like I've said before along the way, somebody's going to ask you, but why does that work that way? And even if you can't remember, then you'll know, you know what, I saw that once upon a day. I can Google it, or I can go back to some notes, or I can email someone and I can find that out for that student. Okay? So I want you to have seen these once at least before you head out there. So the first one actually talks about having a base of an a and raising it to a power of m, and then another base a and raising it to a power of n, and then multiplying those two values together. Do you guys remember how you can combine those into a different notation? Right. We actually would add the exponents together. So when you have the same base, and it has to be the same base, those a's being the same has to happen for this to work. And the exponents may be the same, they may not, it doesn't matter. I can add my exponents together. Now if I have property 1, where when I turn multiplication, I add the exponents. Again, I promise I'm going to explain why in a minute. But if I take multiplication and I turn it into addition of exponents, what do you think is going to happen with division? Yep, we subtract the exponents. So the top exponent gets subtracted, or the bottom exponent gets subtracted from the top exponent. And before I actually write down the rule on number 3, can you tell me how 3 is different than 1? Yeah, I have something that's already an exponent, a to the m, right? And then it's raised to another exponent. Can you also tell me another identifying feature that makes this look different? There's some parentheses. There's one more thing. I don't have 2 a's. You see that? I only have the base listed one time. It's not a base to two, there's not 2 separate bases, right? Up here I had a listed twice, and here a is just listed once. All right, so this one, when I actually have that exponent raised to another exponent, any ideas what I might do with those exponents? Yeah, I multiplied them. 4 and 5 are quite similar. I have multiplication raised to an exponent on 4, and I have division raised to an exponent on 5. What do I do? Right. And I already almost heard someone say the word distribute. We have this sort of feeling that we're distributing that. That's not our distributive property, actually, because our distributive property actually takes multiplication and distributes it across addition or subtraction. But it has very much that same feel to it, where you're applying that exponent to each of the individual bases, right? Yeah. All right, let's take a look at the next one then. It's got the same basic format. If I can do it with multiplication, I can do it with division. So I've got a to the m over b to the m. How do 5 and 6 differ? There's a negative on number 6. Do you guys remember what the negative does? Yeah, it's a reciprocal. It flips the fraction upside down. So it's this equivalent actually to having b over a to the positive m. So I flip the fraction upside down. Then I actually can change the exponent to be a positive exponent. And then I could do the same thing I did on number 5. So this actually takes this and it writes it as b to the m over a to the m. So these are our 6 basic properties. There's a couple more I think we're going to encounter when we're done with my explanation of these. Yes, Kirian?
I've heard an interesting way of explaining it that might work well with kids to describe it, the negative, as an elevator ticket.
Elevator ticket, okay.
So it takes you whichever floor you're not on.
That's cool. You guys heard that before? That's nice. So the negative has this ability to change your location like an elevator would. Very nice. Mnemonic devices are great. Whatever you can do to help the kids remember what operation they're doing is a really good thing. Let me take a little bit with you and show you why each of these works. So you know what the property is because we just went through it. So the first one, a to the m times a to the m is the same as what? This one, right? A to the m plus n. So I want to show you with some numerical examples why that works, right? So the first one has, my example is a cubed times a to the 4. So what is a cubed? Okay, so there's 3 of them, right? What is a to the 4th? Yeah, a 4 times. Yeah, 4 times there. Now, these are just multiplied together. So I have 3 a's times 4 a's, which is a total of how many a's? 7. And how do you get from 3 and 4 to 7? You add them together. That's exactly how simple that process is, and that's why they're not multiplied. It's because I just showed you an example, and that's what happened, right? We do the same thing with division. So we discussed just a moment ago that division becomes subtraction, right? All right, so now I have a to the 4th, which you told me just a minute ago was 4 a's. And I have a to the 3rd, which you also told me was 3 a's. So, now what? Yeah, I can reduce them, right? I mean, that's what we've actually been working on back in section 6.1, is that there's the ability for 3 of those to be reduced, which leaves me with just plain old a, or for the point of what we're discussing, I'm going to write a to the 1. So how do you get from 4 and 3 to 1? Subtract. So that's where that's coming from. The third one, when I have an exponent raised to an exponent, we've got this going on, right? So we have a base and an exponent raised. And we're going to look at a cubed to the second. So a cubed, as you guys said, was a times a times a. And when you raise something to a second power, it means to multiply it by itself. So everything that's written in the multiplication, that parentheses, is going to be multiplied by the exact same thing again. Right? That's what a power of 2 does, is it multiplies whatever you had times itself. So take a look. How many a's is that? 6. And how do you get from 2 and 3 to 6? You multiply. Okay, is this okay so far? All right. Oops. All right, next one is ab to the m, which we said looks like this. A to the m, b to the m. And we have an example of ab to the 4th. So raising it to the 4th means multiplying it times itself 4 times. So far, so good? Now, there's a property of multiplication, and we encounter it throughout Elementary Math 1, and we've already briefly encountered some of the properties that we haven't spoken this one. But the property is called the commutative property. It allows us to switch orders of multiplication. And you guys know this works, right? Because 5 times 2 is the same as 2 times 5. It's a commutative property. It allows us to switch the order of multiplication. So if I do this lots of times, I can change this order to show all the a's at the front and all the b's afterwards. And that's the same thing, right? And if you see that written in that way, you can clearly identify that there are 4 a's and there are 4 b's. So it really is, in fact, true that that power of 4 has the ability to sort of distribute across the multiplication. Number 5 works the same way. In fact, it's even clearer in many regards. It is a to the m over b to the m, because I have a over b times a over b times a over b 4 times. And I don't even need to reorganize anything. I just multiply across the top, and I say, oh, look, there's 4 a's, and I multiply straight across the bottom, and look, there's 4 b's. So this is a to the 4th over b to the 4th. All right, the last one, number 6, turned this into b to the m over a to the m. So one of the things that we can recognize, we sort of did it in general terms a minute ago. But negative 4 is actually just negative 4 times, it's negative 1 times 4, right? So this, I'm going to write this as 4, and I'm going to write this as negative 1 on the outside. So I've just rewritten this. I'm actually using this property, which one was it? This property over here to do this. I'm able to actually say that if I had, for instance, 6, that 6 is 2 times 3, so it could be written like this. I'm just doing this property in reverse. I'm starting here with this something raised to the negative 4, and I'm writing it as a negative 1 and a positive 4. Okay, multiplication factors. All right, so taking a look at this then, I can distribute that 4 because I just learned that that was perfectly fine and appropriate to do so. I can write that as a to the 4th over b to the 4th. And then, as you guys mentioned, a negative Wagner exponent it means reciprocal. I mean, that's its meaning, actually. It means the reciprocal. So it means that I can take this fraction and I can flip it upside down. So it's b to the 4th over a to the 4th. All right, I think I have a couple more for us to take a look at. These are not basic properties, but they're very helpful properties. In fact, when we talk about this first one in Math 1, a to the 0, we just say this is defined to be the number 1. And that's where we leave it. And we don't justify why it works. And the reason we don't is because we aren't talking about rational numbers yet. We're still working in the whole number system. So I want to talk with you about why this works, because this one looks a little bit odd. I mean, let's be honest, right? I turned something that didn't probably even have a 1 into it at all, and now there's a 1 involved. I mean, where'd the 0 go? Where'd the a go? It looks like magic. All right? So I want to talk to you about why this works. And I'm going to do this with the value, let's see what I write down. We'll just do it with a to the m. All right, so 1 is equal to the fraction a to the m over a to the m. Are you guys good with that? Like, it seems like weird, like why would I want to do that? But it works. It's the same thing. I've got the same numerator, same denominator, so that's another way of writing the value 1. If you take a look back at property number 2, what did it say I can do when I have a to the m over a to the n? I can subtract the exponents, right? So my exponents happen to be the same, but I can still write them in that way, a to the m minus m. And what happens when I subtract m minus m?
0.
I get 0. And you could start over there at the a to the 0 and go backwards in this argument as well. So if I'd wanted to, I could have done this and said a to the 0 is a to the m minus m, but that's the same as a to the m over a to the m, and that gets me 1. So if you like that sort of direction of the way that it would go, you could do it from that perspective as well. So it really is 0. I mean, the a to the 0 really is the number 1. That's not just magic. It really does work, okay? On number 8 is very similar to number 6 because it's got that negative exponent going on. So when I write the a to the negative m, this is 1 over a to the m. The difference being that this one didn't look like it had a denominator to start with, right? On problem number 6, that property, you could see the numerator and denominator in the problem to begin with. So when we're seeing that a to the negative third, we can also separate it just like we did when we were justifying the other one. This is a to the third and then to the negative 1, right? And then what does a negative 1 do? Well, it flips it upside down, but there is no down here. So what could I do to rewrite this so that I can see that? Now I can write it in fractional form, whereas it has a denominator of 1. And then I do have that same form that problem 6 or part 6 of these properties had, and I can flip it. So then I can actually write this as 1 over a cubed instead of a cubed over 1 to the negative 1. Okay, so these are the justifications, or at least some justifications. There are others on some of these too, but these are some justifications for why they work. Now, what we're going to actually do is we're going to apply those properties to some specific examples. Okay, so I'm not going to see any written out like 6 A's in a row. That's not what we're going to see happening here. We're going to use these 8 really, properties to actually rewrite some different examples. So on number 6, example 6, we're going to write in simplest form with positive exponents. And let me just say, there is more than one way in many of these problems to do the problem. So you may look at this and say, oh my goodness, that's got to be property number 1. And somebody else may look at it and say, you know what, I really see property 6 written all over that. Now, I don't know that 1 and 6 are the ones you use, but you may use a different property to start with. So somebody tell me what you see when you see this particular example. What would you do first? What would you do?
But I would take B because you can reduce it. That's not reduce.
Reduce is
B,
okay.
Yeah.
Yeah.
The 4 and the 2, so
Okay.
B squared disappears and it's A or B squared.
Excellent. So the first thing you see has to do with the b's, right?
Yeah.
I have a b to the 4th on top. I have a b squared on bottom. So one way to do that is to use that subtraction property, which was property number 2. It says that I can take 4 minus 2, right? So this can actually be rewritten with b, and then it's 4 minus 2. So just in case somebody wasn't seeing what I was saying, that gives me b squared. That works very nicely. How about the a's? What am I going to do with those? You could. So what do you mean by flip? Well, I agree that the a to the 3rd could move up. I'm not so sure that a should move down. So what's different about the a to the 3rd, that part of it, that I say it can move up than the other one? Yeah, so if we move things between the numerator and the denominator, it changes whether they're positive or negative. So one way to handle this is to leave the a where it is, and then simply move the a to the negative 3 up. And that's very much using property number 8 that we just did. Okay. Then what would I do? Because that's not simplified. I still have a as 2 written down 2 times. Yeah. So this has a power 1, right? So then I can add the 2 a's together, so I have a to the 4th. Did anyone think to do something different than simply moving the a to the 3rd up? Did you think of it a different way?
I guess you could do A to the 1st plus
Close, yes. I could do it much like I did with the b's. So I could write a to the 1st like you're suggesting, and then it would be minus negative 3.
Oh, right.
Right?
Yeah.
So we would have minus because it's a fraction. You've got one of them on top and the other one on bottom, so we're going to subtract. That will actually result in it being a to the 1 plus 3, right? Because we have the opposite of a negative. 2 negatives is positive. So that's another way of doing it. Yeah. So we could actually treat it much like we did the b's if we wanted to in that way too. It'll still give the same answer though, yeah? Okay, great. Now, b is different. How is b different than a? There's several things. Somebody give me one of them. There's multiplication involved, yeah. There's numbers. I think that's kind of the biggie, right? There's numbers. There weren't numbers in the last one. What else?
Did you say parentheses?
I see some parentheses. That's very good. I have fractions actually in the problem instead of just the base being an a or something like that, what appears to be a solid value.
I have kind of a random question.
Yeah.
How do you decide whether to do the multiplication marking as like the X or the dot? Because I know like when I was younger.
It's just textbook specific. Yeah. At some point in the late elementary school, early junior high, you stop using an X between, and you usually do it because you've hit X as a variable, and there's this sort of a weird problem because you've got 2 meanings for what looks like the same thing. Yeah. So about the time you hit algebra is usually when you see that notation change.
So it's not super particular.
No, it's usually just wherever the textbook changes it. Yeah. There's something else really weird about this one. They are multiplying. There's something else.
The simplification.
Hmm?
There's a negative 6.
I do have a negative 6. That's true. Something else.
The 4 over 25 can be simplified.
Okay.
Well, not
It
really.
can be, but you can make a stronger statement than the one you just made. Carrie Ann?
The first one squared is the second.
And that's going along with that simplifying issue. It's stronger than those statements, though, than what you guys are making. Their statements are true. Everything you guys have said is great. But the real problem with this is that if I don't change them, I can't combine them at all. All those properties that talked about combining exponents and things like that had to do with the bases being the same. And right now, 2 over 5 and 4 over 25 are not the same. You guys see that? So I can't use any of those properties until I get them to actually match. So I have to get them to match. I not only can I must. Right? So it's a stronger statement than I have the ability to. I have to, or I'm not going to be able to simplify the problem. Now, 2 over 5, if I square it, like Kirian said, it becomes 4 over 25, right? But you can't just randomly square pieces of a problem, all right? Or it changes the value, agreed? Right? If I just decide I'm going to square the number 5 and it becomes 25, well, that's different than the value 5 was to start with. So instead of dealing with the 2 over 5, what are your thoughts?
I was going to say, couldn't you write it as 2 over 5 to the second times, 2 over 5 first?
For which part? Like I did, or did I do something that wasn't what you intended?
No, that's right.
Okay, but then that means I changed this first value of the problem. I changed it from 2 over 5 to 2 over 5 squared. That changes the value.
No.
Multiply what, Hannah?
5 by 5, 2 by 5.
That's the same thing as squaring it, but if I multiply the 5 on the denominator by 5 and the 2 on the numerator by 5, that's not going to give me an equal fraction. Square the what?
So it would be like 2 over 5 squared, and then you have to square the 3, 2.
Like that?
Yeah.
I've actually created the problem to be worse now, because now I've squared it twice.
Okay.
No, but by... Hold on, because I'm confused. Because by the first property we talked about,
Mm-hmm.
a to the n times a to the n, you add m and n. But is it different with fractions?
I think what you might mean me to say is to write down that I can do this. Is that what you want?
Yeah, that's what I said.
Okay.
That's what I meant to say.
Okay. That works, but this problem still is that it doesn't match the 4 over 25. It's a true statement. It just still doesn't match the 4 over 25.
Take the, like, not square root it, but make it 2/5 squared to raise to the -6.
This piece?
Yes.
Okay. So you want me to change the 4 over 25 to 2/5 squared?
Yes.
Like this? Do I have that right? It's Allison, right?
Yes.
Do you guys agree?
Like, I don't understand.
So we haven't changed anything on the first piece. We just changed the second piece. So what we're going to do, that's a good first step, Allison. That's what I would do too. Is that we're changing the fact that we had a 4 on top. So this was 4 on top, right? And we're writing 4 as 2 squared. And we're rewriting that 25 as 5 squared. And you can write it like I just said, instead of it writing as a fraction 2 over 5 squared. If you want to write it as 2 squared over 5 squared, that's the same. Yeah. That's a big step, because now I have bases that match. They both say 2 over 5. Yes?
Okay, so you did the, like, 4 over 25 and
Mhm.
changed that to 2 over 5 squared to make it be equal with 2
Yes.
over 5. Oh, okay.
Our goal is to have this value and this value, which are the bases of the exponents, matching.
Oh, okay.
So instead of trying to make the base bigger, which was creating problems because we were actually changing the value, we created the numbers that looked bigger, the 4 and the 25, to be rewritten in a condensed, smaller way.
Okay.
Mhm. Is everybody good? Shayna?
So then, now do you do the 3 and 2 together, and then do the -6 part?
Good question. So what's first? Am I going to deal with the 3 and the 2 as exponents first, or something else?
Do you have to?
Well, don't you usually do what's in the parentheses first?
Yeah, I need to deal with the fact that those parentheses are going on first. So the
-6 to 2.
right, this is the first piece to deal with. Yeah. So I'm going to have 2 over 5 to the third still. And now I'm going to have 2 over 5 to the what? Negative 12th. We don't add them, we multiply them. Yeah, negative 12th. Then what?
Now you can add them.
Now I can add the 3 and the negative 12 to give me negative 9. And this is a much more condensed form than I started with. Agreed?
Yes.
This is much better, but I'm still missing one piece. Carrie Ann first. Yes, right. So the directions actually said something about only having positive exponents. Agreed? So this has a negative exponent. So how do I get it to be positive? Carrie Ann said I should flip it. Yep. So this is going to be 5 now over 2, not 12, 2 to the 9. And there's no reason to make these powers to the 9 actually operate. That's not what you're asked to do. Leaving it in exponential form is the expectation, okay? If you want to confirm that this works with your calculator or something like that, just to make sure, that's fine. But there's no reason, and I'm not asking, and please don't, please don't multiply these to the 9th power, okay? This is good. So we've got 5 over 2 raised to the 9th.
So should we leave it as an improper fraction?
Absolutely, yes. Yeah, we really don't want to write this as 2.5 to the 9th. Not sure I've ever seen it left like that with a mixed number, so we'll leave it as an improper fraction. Yeah. All right. These are a little different because they actually want us to solve an equation, right? They've got the equal sign in it, and they're telling us they want us to solve n. That means figure out what in the world is n. All right? Now, we're still going to use the properties in order to do that, starting with part A. So take a look at the left-hand side to start with. 2 to the n and 2 to the 7th. Our properties tell us I can do what?
2 to the n plus 7.
Good. I can add the n and the 7. I agree they don't really combine into a smaller form, but I can write it as n plus 7. Yes?
I was going to say, for a 64, make it 2 to the, I don't know what it is, 2 to the something to equal 64.
Does anyone know what it is? Bigger. Smaller.
Is it?
It's 6.
I was
Yeah.
thinking.
So 2 to the 6th. 2 to the 5th is 32. All right, 2 to the 6th is 64. And that's exactly what we want to do. You were totally right on the mark on that. We want them to look like, the two sides to look alike. We want them to have the same base. If they have the same base, then we can sort of ignore the base. We can only compare, or we can reduce this to comparing the numerator. Not the numerator, excuse me, the exponent. So you want to tell me what to do next? Tell me.
Yes. N plus 7 equals 6, and then solve for n.
So what will n be? Negative 1. If I subtract the 7 from both sides, I have 6 minus 7 is negative 1. So let me go through the little steps again. We're able to combine the left-hand side using properties. It was property number 1. And then we're able to rewrite the right-hand side as a base 2 to a power. Okay? We need the right-hand side and the left-hand side to match. If they don't match, we can't compare the powers because the bases need to be the same. So once we get the bases the same, which we did, then we can sort of ignore them because they don't affect anything. They match. And we just compare the numerators now. I said it again, exponents now. This is much like when we're working with fractions, right? Where when we get the denominators the same, we can just compare the numerators.
Is that a specific property, or are you just disregarding it because you don't have
It is a property. It's called the one-to-one property, and it has to do with the fact that these are both functions and they work on an XY axis. You're not going to encounter that part of the reasoning why when you actually teach this piece of information to kids. But there is a reason why. It is the one-to-one property of functions. Yeah. All right. The second one here, part B here. Well, first of all, it's different because I don't have an equal sign. Agreed? That doesn't affect the problem. It just means the answer is going to have that symbol in it. Okay? So that's not going to actually change what I'm doing. I do still need to get them to have the same base on both sides. And right now, on the right-hand side, I've got a fraction. So I don't want there to be a fraction on the right-hand side because the left-hand side doesn't have one. So any idea about how I could not have that 81 in a denominator? Okay, so I heard like 4 answers and I didn't hear any of them clearly. So, Allie? Okay, do the reciprocal. So what would you like me to write on the right-hand side?
I have no idea.
Okay.
It's 81, right?
It's not negative 81, but...
Oh, that's what I said.
There's the negative. Okay, so I do have a negative, but it's not negative 81, right? Like 1 over 81 is not the same as negative 81. but it is 81 to the negative 1 power. Right? Negative 1 power is what does the reciprocal. Okay? So this is really good. Still doesn't match. So what in the world now am I going to do with the 81?
Divide it by,
Close.
I mean, 3 to the something is.
There we go. I need a base of 3. It's got to be the same as the other side. 3 to the 4th is right, Allison. And you're welcome to use your calculator to do a little trial and error. That's a perfectly legitimate property. I mean, like, there are not property, problem-solving strategy. So we want this to be 3 to some power, so try it. Take 3 and try 3 to the 3rd, 3 to the 4th, 3 to the 5th, until you find the value it is that you wanted. 3 to the 4th will work, but I still have a negative 1 exponent.
So then, isn't it just like the problem before where you combine those?
Almost, but I don't have just 3 so far. I've got 3 to the 4th to the negative 1, which is 3 to the negative 4.
Yeah, that's what I was saying.
Yep.
Sorry, combine the exponent.
Yep. Yes, it's like we did on the very first step on the last problem, right? Different property, though. This is property 3. So I've got 3 to the negative 4th. Now what? Now I have 3's on both sides. That's good. Yeah, that 1-to-1 property that Allison was asking me, is that an actual property? Yeah, it actually is. And so I can ignore my bases now. I have n on the left. I have negative 4 on the right. What's going to go between them?
Since it's negative, doesn't it?
No. Less than or equal to. The symbol stays the same all the way down. It was less than or equal to at the beginning. It's less than or equal to at the end. What you're remembering is that if you divide or multiply by a negative value, it switches the direction. But I didn't divide or multiply on this problem, so I don't have to change the direction. So my value is that n is less than or equal to negative 4. And you could check to make sure that works. How could you do that? What could you do to see that this really worked? Yep, you could plug in negative 4, and if you take your calculator and you put 3 to the negative 4 in, press enter, and you put 1 over 81 in, and you press enter, they should match. If you, that verifies the equal to part. If you wanted to see that it's less than or equal to, like you really had the right number, right, it really is 4 as opposed to 6 or something like that, you could try something smaller than negative 4, maybe negative 5. So you put in 3 to the negative 5 on the left. Press enter. Put in 1 over 81. Make sure that 1 over 81 really is bigger than 3 to the negative 5. You could test like that. Yes? Yes. All right, example 8. This is an approximation problem. Oftentimes, approximation is good enough to actually state your answer. And so this is an example where you might want to do that. Approximate the following product. If I have 20 and 1/3 divided by 9 and 7/8, what values could I use that would be easier to work with than the values that were given if approximating is all I want to do? Yeah. This would be much easier if it simply said 20 divided by 10, wouldn't it? And it's going to be very close. What is 20 divided by 10? 2. So this is approximately 20 divided by 10, which has the value of 2. All right, example number 9. Talks about something that you would actually see happen. You wouldn't see it happen with fractions. You'd see it happen with percentages these days. Let me give you the context first, and then I'll tell you what I mean. Jasmine's reading a book. She's finished 3/4 of the book and has 82 pages left to read. So maybe she's approximated she's finished 3/4 because she looks at the spine and she says, it looks like I'm about 3/4 done. That could be an example. Maybe she's using something like a Kindle, where it doesn't tell you what page number you're on, but it tells you you've finished 75% of the book. Do you guys ever see books on Kindles or laptops like that? That's how it tells you. It does not tell me what page I'm on in the books that I'm reading right now. It just tells me I'm 2/3 of the way done, but it tells it to me in percentage form, 67% or whatever. And then it also tells her she has 82 pages left to read. Now, the Kindle wouldn't tell you that, but she could actually figure that out if she were working with a paper copy, or if she were working with a paper copy and a Kindle copy or something like that, she might be able to know she has 82 pages left. Okay, something like this. The question is, how many pages has she read? So there's several ways to do this problem. somebody give me an example of what you're seeing on how in the world would you set this up?
3 is equivalent to 82 over x, and then plus multiply.
Okay, you're really close. It would. Why 1/4, Allison?
Because she has 82 pages left, and she also has 1/4 left.
Excellent. So you have to be sure that you're comparing the right things. I really like this method, Hannah. I think it works really well. But we want to make sure that we're comparing what she has left and what she has already done. So 3/4 is what she's read, right? But the 82 over something is what she has left. So we want to make sure that they match. So one way to fix that is exactly like Allison suggested. We could write this as 1/4. So she has 1/4 of the book left, and she has 82 over somehow a number of pages left. Does that make sense? So if you're doing it this way, this is a comparison. This works great. And then what would we do?
Multiply 82 by 4 and then divide by 1, but it's just amazing.
All right, so in essence, we're cross-multiplying, right? Or we're multiplying by the 4 to get it out of the denominator and the x to get out of the denominator. So this would actually end up giving me 82 times 4, which is what? 300 what? 28. 328 what? Pages. Now, we want to be careful to answer the question we were asked. What question are we actually asked? How many has she read? Like, what page number is she on, so to speak? How many has she read? Is that this number? Now, what is this number? All right, so this is the pages in the whole book, right? So if I go this route and I get to this point, this is fabulous. I just need to make sure that I'm answering the question. So I have 328 pages in the whole book. How am I going to answer the question that I was actually asked? Yeah. Minus the 82. 82 is what she's got left, right? So we can take 328 minus my 82, and what do I get? 246. And this is my pages read. Be very careful that you answer what's asked, because if you just stopped just shy, you'd have been almost there, man. But you really missed answering the question correctly too, because you weren't being careful of the reading. Okay, one more problem. Al gives half his marbles, that should say to Bev, not ought Bev. To Bev. Bev gives 1/2 of these marbles to Carl. Carl gives 1/2 of these to Danny, and Danny was given 4 marbles. The question asks, how many did Al originally have? Again, there's more than one way to do the problem. What are your thoughts?
4 times 2 times 2.
Okay, so you started out with talking about Danny, right? So Danny has 4 marbles. Agreed? And who came before Danny? Carl?
Yeah.
So if Danny has 4 marbles, and we assume he had none to begin with, because that's the way the problem is sort of leading us along with this, right, to believe, then how many did Carl have before Danny got his 4 marbles? He had 8. Okay, so he had 8 before he gave things away. He has 4 now, agreed? So be careful that if they ask the question that way, we just want to be obvious that we're answering the right question. Okay, so before Carl was Bev. Bev gave those 8 to Carl, so how many did Bev have? She had 16 before. How many does she have now? She has 8 now. She gave half of them away. And then Al came before Bev, so Al has 32 to start with before, right, originally, which is actually what I'm asked for. If I were asked how many does Al have now, it would be 16. Yeah. So being very careful about the language that is being used. Al had 32 marbles. I'll put marbles in here. Before he started giving them away, or originally.